want to give you orange, but I don't have a whole orange to give you. I want to give you a portion of one orange. Choose between these two settings. I bring an orange and I want to give you some part of that orange. Which of these two settings will you prefer that I use to give you the part of orange I want to give you? First, I bring the orange and break it into two and give you one out of the two portions. Just keep thinking about it. Compare it with that I bring the same orange and break it into 10 and give you 5 portions. In the first case, I offered you 1 out of 2 portions of the same orange. In the second case, I offered you 5 out of the 10 portions of the same orange. Which of these two will you accept? Is any of them better than the other? Is any of them bigger in size than the other? While you are thinking, let me assure you that there is no difference between these two. That takes us to the third lesson objective of this lesson, and that is equivalent fractions. In this section, we learn the meaning and how to get equivalent fractions from existing fractions. Please follow through as I do that. In this section, let us learn the concept of equivalent fractions and lowest terms. What are equivalent fractions? When do we say that a fraction is in its lowest term? First, let us start with equivalent fractions. Again, I ask, what are equivalent fractions? Let me use this diagram, this circle, to explain what equivalent fractions are. Please pay attention closely to this. What you are seeing is a circle broken in half. This diameter breaks this circle into 2 equal parts. What will you call one portion of this circle? Okay, as you are thinking, let me name each portion, and after I do that, compare what I have written with what you are thinking. Please watch. Here it comes. Each half or each portion is equal to 1/2, or just half. 1/2 here, 1/2 here. It means that this portion is called 1/2 or half, and this portion is also called 1/2 or half. Now, again, watch what happens next. Now, notice what has happened. This circle is now broken into 4 portions. Before now, it was broken into just 2 portions. I remember that the whole of this portion from here to here, then this way, was called 1/2. Let me write the former name of that portion before we proceed. And now we recall, it was 1/2. Now back to what it has become. Is this section still 1/2? No. Why? It is because we now have 4 portions, no longer 2. Earlier, it was 1/2 because there were only 2 portions and only one was picked. That is, this side was picked. This side too was picked, but from now, for us to understand the concept of equivalent fractions, let us not concentrate on both sections. After all, the 2 sections or portions are just the same. So we face one. Whatever applies to this part applies to this part. So permit me to continue using this part until we get to understand fully the meaning of equivalent fractions. Let's make progress. Again, Do you still call this side 1 over 2? No. What is now called? Please find out. And here it comes. Each of these two portions is called 1 over 4. Let us not forget that it is the whole of this that we called 1 over 2. So it is still 1 over 2. But that 1 over 2 is now further broken into two portions. This portion and this portion make up the former 1 over 2. It therefore means that this 1 over 2, when broken into 2, will give us 1 over 4. Therefore, this portion and this portion are called each 1 over 4. Why? It is because we have 4 portions in all. 1, 2, 3, 4. So this is 1 out of 4 portions. This is also 1 out of 4 portions. In fact, each of these 4 quadrants is called 1 over 4 because each of them is 1 out of 4 portions. Now, are you aware that if you join this 1 over 4 to this 1 over 4, that the result is still 1 over 2? What it means is that nothing changes if we join these two together. It means that 1 over 4 plus 1 over 4 will be equal to 1 over 2. I just believe that you are following the argument here. Now, back to what I was saying earlier. What are you still going to call this place? It is still 1 over 2. But because it has been broken into two portions, and now if you pick these two, they are still equal to 1 over 2. But these two are being picked no longer out of 2, but out of 4. So if you pick these two portions, which are still equal to the former 1 over 2, we pick them out of 4. Therefore, right now, we have a new name for these two portions put together. What is it? The name should be 2 over 4. I hope you're following. Let us write it. And here it comes. The new name of these two portions when put together is now 2 over 4. And its former name, when it was just alone without being divided, was 1 over 2. Let us do more divisions to see what comes up next. And here is what has happened. This circle is now broken into 8 equal portions. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. Don't forget that in the beginning, the same circle was broken into 2. Next, it was broken into 4. And now, it has been broken into 8. But one thing stands constant. We are still concentrating on this portion from here through this region, then like this, just this portion. Originally, it was equal to 1 over 2 when it was broken into 2. The same region, the same portion, became known as 2 over 4 when this circle was broken into 4. And now that it is broken into 8, what is now the new name of this region? To get its name, check how many portions now make up that region. That region is now made up of 1, 2, 3, 4 portions. Then if you pick these 4, then you have created the size equivalent to the original 1 over 2. Then these 4 were picked out of 8. The implication, therefore, is that the name of this original portion has now become, what is it going to be? Let me write, and you compare what I have written with what you are thinking. Please watch out. Yes, the name is 4 over 8. It means that the new name for this portion, original portion, is now 4 over 8. Can we divide this circle further? Can this circle be broken further into more portions? Let's try. Yes, it has become possible. We've been able to divide the same circle into how many portions? Please, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 portions. How? Each of the former 8 portions was broken into half, making all now 16 portions. Now back to our major concern. What is it? We want to keep on describing in different ways this portion from here to this point, then through this way. That is this region. First, we named it 1/2 when the circle was broken into 2. Again, we named it next 2/4 when this same section or portion was, when the entire circle was broken into 4. We named it 4/8 when the entire circle was broken into 8. Now that the circle has been broken into 16, how many portions now make up the original portion we have been keeping in mind? This entire portion, how many more smaller portions have been made out of it? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. If you add each of these 1/8 portion, that is, each of these portions is called 1/8. If you add all together, they are still equal to the former 1/2, still equal to the former 2/4, still equal to the former 4/8. But don't forget that it now has a new name. What is it? 8 portions. Out of how many? 16. Let us write it. And here it comes. The name of this portion is now 8/16. Now, let us use these names to explain the concept of equivalent fractions. Now, let's assume that this circle is just one orange. Initially, I broke the orange into 2 equal portions, and I chose this right-hand side portion, that is this portion. Okay? And I named it 1/2. That is 1 out of 2 portions, 2 equal portions. If I had placed that 1 out of 2 portions on a scale to check its mass, if I had recorded the mass of this 1/2 and then compare it with the mass I will get if I divided the thing into 4 equal portions and picked 2, meaning the mass of this section, this portion, when I picked only 1 portion out of 2, compared with the mass of 2 portions picked out of 4, that is 2 portions picked out of 4 portions, and compare it with the mass I got if I broke it into 8 and picked 4 portions, and also compare it with the mass I got when I broke it, like I have just done now, into 16 and pick 8. That is, if you compare the masses of 1 out of 2 portions, 2 out of 4 portions, 4 out of 8 portions, 8 out of 16 portions, which one do you think will be heavier? Certainly, none of them will be heavier than the other. Do you agree? You should. The reason you should agree is that the size of the portion never changed. The size of the portion never changed. Only one thing kept changing. only the number of portions we got from that section kept changing from 1 to 2 to 4 to 8. Even next, we can get 16 out of 32, and in that order until we get infinite number of portions from this one orange. It therefore means that this 1 does not mean the mass. Instead, it means number of portions. This 2 also does not mean the mass, but number of portions picked. This 4 is not the mass, but number of portions. Therefore, all of these things, both numerators and denominators, do not indicate the size from which we picked and the size we picked. Instead, each of them tells us how many portions picked from how many portions. Therefore, the mass of this portion remained the same, but number of portions kept changing. Because of that, we now conclude that though number of portions kept changing, the mass remained constant. If the mass of that one portion of the orange is the value attached to it, since all now have equal mass, we now see that or conclude that the value of 1/2 is the same thing as the value of 2/4, the same thing as the value of 4/8, the same thing as value of 8/16. It therefore means that 1, 2, 3, 4 ways are just different ways of describing one particular portion. As a result, they are all equal in value. Let me put a sign between them or between any two successive fractions to show that they are equal in value to one another. Let's see. And that is it. This is a sign of equivalence. It therefore means that 1/2 is equivalent to 2/4, also equivalent to 4/8, also equivalent to 8/16. At this point, how then do you think you should define equivalent fractions? Think about it before I write the definition, so you can compare what you have been thinking with what I will write. Let's see. And here comes the definition of equivalent fractions. Equivalent fractions are two or more fractions which may have different magnitudes of numerator and denominator, but possess the same value. I hope the meaning is clear to you. Okay, with these fractions in mind, don't forget that we said that all these fractions are equivalent to themselves or to one another. This is a fraction. This is also a fraction. This is also a fraction. This is also a fraction. So we have more than two fractions here. It is never compulsory that each time you are talking about fractions which are equivalent that you must have 4 to compare. A minimum of 2 fractions will be needed to kind of highlight the concept of equivalent fractions. Even if it is only 1/2 and 2/4 that we are isolating, that will be enough for us to see the message behind the concept of equivalent fractions. But there are 4 here. It's just a mere choice. We can have 3, we can have 2, we can have 4 or more. Let's go on, please. All these fractions are equivalent. They possess different numerators. 1, 2, 4, 8. They also possess different denominators. They are 2, 4, 8, and 16. Yet, all of them have equal value. What is the value? Don't forget that in this case, the value is the mass. It doesn't mean that in every case that you discuss or think about equivalent fractions that mass must be the value you are talking about or you are going to bear in mind. There will be other ways to check the value of anything. Every individual determines the value he attaches to anything. It must not just be maths at all times. That maths is serving us in this case doesn't mean that maths is what you have to hold on to each time you want to think about fractions which are equivalent. Therefore, these four fractions are equivalent fractions. They possess different magnitudes of numerators and different magnitudes of denominators, yet they all have equal value. Because of that, they are called equivalent fractions. If you are still grappling with the concept of equivalent fractions, see it another way. What other way is that? Just imagine that, like I said earlier, this is an orange. This same orange, if you break it into two and pick one, keep it. What if you decide to break it into four and pick two? Is there any difference in the value of the first portion you picked and second portion you picked? Breaking something into two and picking one is just the same thing as breaking the same thing into four and picking two. In fact, the same thing is what you're going to get if you break the same orange into 8 and pick 4. And yet, the same value is what you're going to get if you choose to break the same orange into 16 and pick 18. In fact, it is least laborious to choose this one, because instead of doing it in this way or this way or this way, simply do it like this, except you have a special reason to break it into 4. But if you know you're going to choose 2 out of the 4, why the labor? Just break it into 2 and pick 1. That we shall tell more about when we go to lowest terms. But I hope that this one will help you understand that this and this are equivalent. This and this are equivalent. This and this are equivalent. And this is equivalent to each of these fractions. Now, let us talk about how to obtain equivalence fractions. That is, if we write a fraction and we want to get other equivalent fractions from that singular fraction, what must we do? Let's talk about it. Now let us see how to obtain equivalent fractions. To do that, let us remember what we saw just recently. We recall that these 4 fractions are equivalent to one another. It is this 1/2 that produced the other 3. We're going to make use of consistent observation to find out how to obtain equivalent fraction or fractions from one fraction. The number of equivalent fractions we can get from one fraction is infinite. The type of fraction we get that is equal in value to a given fraction depends on a purpose, depends on objectives set before us. Depending on real-life situations, we can target certain equivalent fractions to be created out of existing one. Let us assume that 1/2 is given to us, and we are told to obtain other equivalent fractions from it. Like I said earlier, we have infinite number of ways of getting that. But before even we settle for that, we have to learn through observation how to get equivalent fractions from existing one. The question is, how did this become this? We remember the circle, which had to represent an orange. But it does not mean that every time we are to obtain fractions, which are equivalent from one fraction existing, that each time we do it, that we must draw an orange and start breaking it into pieces. It is too laborious. So at this point, we want to learn how to get equivalent fractions from existing one without use of diagrams. To do that, again, let us notice how this became this, how this became this, how this became this. It is also possible to notice how this became this, and how this became this, and how this became this. Each of them is possible. Each of these fractions is equivalent to each of the remaining three. That is just truth. Let us start with this 1/2. How did 1/2 become equivalent to 2/4? We're going to do it by observation. And if what we observe becomes consistent, it becomes a law for obtaining equivalent fractions. Let's see. And here we come. This 1/2 is equivalent to 2/4. Without using a diagram, how do we know the way this 1/2 became equivalent to 2/4? Like I said earlier, let us do it by observing something. We observe here that this 1, a former numerator, has become 2. This 2, a former denominator, has become 4. We then call this 2 new numerator and call this 4 new denominator. It is this 1 that turned into 2. It is this 2 that turned into 4. Something must have happened, or something should happen to this 1 to make it become 2, and something should happen to make this 2 become 4. After testing, we realized, or I realized, that this 1 turned to 2, not by addition, not by subtraction, but by multiplication. I observed that this new numerator can be gotten by saying this former 1 times 2. That is this 1 times 2. And that gives us this 2, which is here. Since 2 is the factor that multiplied this 1 to give us this, that same 2 is what is going to multiply this to give us this. This is not like imposing a law on this. Instead, it's like a statement of what we observed, or what I observed, in determining how this turned to this and how this turned to this. This multiplied 2 to give us this. This also multiplied 2 to give us this. That means that new numerator is equal to 1 times 2, which is 2. And new denominator is equal to 2 times 2, and that is equal to 4. Now, let us check whether we are correct by testing how this became this, because I said that this is equivalent to all other three. In fact, each of them is equivalent to all other three. Let us see how we can match what we observe, checking how this became this with this first observation. Please, let's continue. And here comes the second observation. That is, this is equivalent to this. That is 1/2 is equivalent to 4/8. Again, we ask, how did this become this? Like we did in this first case, let us try it out by checking how 1 became 4 and how 2 became 8. Certainly, addition and subtraction will not work. You can confirm it yourselves. Now, how did 1 become 4? 1 times 4 is equal to 4. So this 1 became 4 through this process. Again, how did these 2 become 8? By multiplication, 2 multiplies 4 to give us 8, which means that we got this 8 through this process. Have you seen consistency in what we observed in these first and second tests? Surely I have seen something. And even if we come out to start saying something like 1/2 equivalent to 8/16, we discover that the same thing is going to be observed. Each time we observe a consistency in the way number operations turn out, that consistency becomes a law. Something has become consistent in these two number operations. What is it? Please permit me to write that observation. Later, you compare it with what you were thinking. Don't forget, I asked, what have we observed in the way this turned to this and in the way this turned to this? That which observed will be a law to obtain equivalent fractions. Let me write that law, which is a consistent observation. Please watch out. And here comes the formula or the law regarding how to obtain equivalent fraction from an existing one. It says, to obtain equivalent fraction from an existing fraction, multiply or divide the numerator and denominator by the same number. I hope what I said here is clear to you. Possibly, one thing is confusing you or adding to your confusion. I said divide. Are you surprised? If you are surprised, that is justifiable. Why? That is because in both observations, this one and this one, we used multiplication to turn 1 to 2. The same thing was used to turn 2 to 4, to turn 1 to 4, and to turn 2 to 8. In both of them, we multiplied by one number. Like here, 2 multiplied 1 and 2 multiplied 2 to get us these two. Here, 4 multiplied 1 and 4 multiplied 2 to get this. Which means I multiplied both the numerator and denominator by the same number. What was that? It was 2. Here, I multiplied both the numerator and denominator by the same number. What was that? It was 4. See it here, 4, 4. Here, 2, 2. That's why I said multiply this numerator and denominator by the same number. I just skipped this divide, but it is a part of the law. Now back to it, believing that you now know that of multiplication. You may ask, did we ever talk about division here? Please, let me put it to you that this division is a reverse process. Is it possible that we invert this statement so that with that we get to know that division is also a way of getting fractions which are equivalent to existing one? Yes, let's try and do that. Now see the same two statements made differently. This 1/2 was here before. This 1/2 was here before. And 2/4 was here. And this 4/8 was here. I hope you recall. Has this statement become wrong simply because 2/4 now comes first? No, it is still correct. In every statement of equivalence, anyone can come first. If 2/4 is equivalent to 1/2, how does 2 turn to 1 and how does 4 turn to 2? That is, how can 2 become 1 and how can 4 become 2? In fact, that is where we talk about this division. If we divide this 2 by 2, we get 1. Divide this 4 by the same 2, we get this 2. So divide by 2, divide by 2. That is, divide numerator and denominator by 2. That's a common factor. You get this 1 over 2. The same thing applicable here. 4 over 8 is equivalent to 1 over 2. How did this 4 over 8 become 1 over 2? The same thing happened. When 4 divides 4, we have 1. When the same 4 divides 8, we have 2. Because of that, this word divide is just appropriately placed. Now you see the reason why I said multiply or divide. Again, to obtain equivalent fraction from an existing fraction, multiply or divide the numerator and denominator by the same number. When do we multiply and when do we divide? We multiply if we want to get equivalent fraction having higher values of numerators and denominators. We divide if we want to get equivalent fraction having smaller values of numerator and denominator. With these highlights, I believe that you've known how to get or how to obtain equivalent fractions. But it is important we take a few examples to make our understanding even more solid. Let's see more examples. And here come the more examples. The first one is about creating equivalent fractions from 3 over 4. All of these fractions are equivalent to one another and to 3 over 4. 3 over 4 is equivalent to this, this, and this. As we have been taught before, something happened to 3 to make it become 6. And the same thing happened to 4 to make it become 8. So 3 times 2, 6. 4 times 2, 8. So this is equivalent to this. Again, 3 times 3, 9. 4 times 3, 12. Therefore, 3 over 12 is again equivalent to 9 over 12. I just chose 2 to be multiplied by 3 to give us this 6. Because there is no instruction, so I choose any number from list of numbers in existence. But if I have something like an instruction given to me as to which number to use, I have no business with numbers apart from that one given to me. But now that there is no such instruction, I'm choosing just a number. I chose 2 to multiply 3 and 4 to get 6 and 8. Let me choose 3 to multiply 3 and 4. That will give us 9 over 4 over 12. I will choose 4 to multiply 3 and 4 to give us 12 over 16. That is 3 times 4, 12. 4 times 4, 16. Similar thing happened in these other examples. Let's go on, please. 2 over 5. I chose 2 to multiply up and down to give us this. 2 times 2, 4. 5 times 2, 10. Now I choose 3 to multiply up and down to give us this. 2 times 3, 6. 5 times 3, 15. Now I choose 4 to multiply 2 and 5 to give us this. 2 times 4 is 8. 5 times 4 is 20. Therefore, 2 over 5 is equivalent to all these 3. Let's see the last example. 4 over 5. Something multiplies 4 to give us 8. The same thing multiplies 5 to give us 10. It is 2. So 4 times 2, 8. That 2 was chosen. 5 times 2, 10. Let's multiply 4 by 3 and multiply 5 by the same 3 to get this. That is 4 times 3, 12. 5 times 3, 15. Next, let this be equivalent to this. 4 multiplies 4 to give us 16. Like before, the 4 was chosen arbitrarily, not in obedience to any instruction, just for practice. Again, 4 times 4, 16. The same 4 times 5 is this 20. So this way, 3 over 4 has produced other fractions equivalent to it. 2 over 5 has produced all these fractions equivalent to it. And now 4 over 5 has produced these 3 other fractions equivalent to it. Please check out for an exercise. Find out if you can get equivalent fractions from existing one. And here comes the checkpoint. It says, using factors of 2, 5, and 7, obtain 3 other fractions equivalent to each of the following fractions. That is, using common factors of 2, 5, and 7. Obtain 3 other fractions equivalent to 1 over 3, 3 over 5, 2 over 7, 1 over 4, 3 over 4, and 3 over 8. What if a number is unknown in a statement of equivalence? That is, a statement of equivalence is made, and in that statement there exists a number which is not known. What can be done to get that number known? That takes us to how to find missing parts of equivalence. Let's go on, please. And here we are faced with a case of missing parts of equivalence. This is a statement of equivalence. Please permit me to use this case to explain how to get a missing part of statement of equivalence. 5 over 6 is equivalent to x over 18, also equivalent to 25 over y, also equivalent to z over 42. In this statement, we have 3 unknowns. They are x, y, and z. In 2 cases, we have numerators missing. That's here and here. And in 1 case, we have denominator missing. That is just this one. But one thing is common to all. There are missing parts of this statement of equivalence. And to make it possible for us to find the missing parts, one of the fractions must be known, and it is this first one that is known. 5 over 6 is known. It takes one of the 4 fractions to be known for us to find others. Alright, now at this point, how do we get the value of this x? How do we get the value of this y? And how do we get the value of this x, this z? We should not forget that equivalence, in a sense, is also equality. To do it, we break this multiple statement or statements of multiple equivalence to statements of simple equivalence. That means to get this x, we equate just this fraction to this. To get this y, we equate this fraction to this first one, which is known. To get this z, we equate this fraction to this first one, which is known. That means that one way to do it is to ensure that we equate each fraction that contains the unknown to one common fraction that has both sides known. Please let that happen. Now see it. I've just broken this statement into simple statements of equivalence. First, 5 over 6 is equal to x over 18. See it here. Second, 5 over 6 is equal to 25 over y. See it here. Next, 5 over 6 is equivalent to z over 42. See it here. It is better this way, so that with each of these statements, we can get the unknown. There are two known methods of getting the value of this x. The first method is the method of solving equations. Second method is trial and error method. Because it is supposed that you've not been taught equations, let me use second method, which is trial and error. Now follow me as I use it to find the value of this x. How do I do that? I ask myself, this 6 became 18. How did this 6 become 18? By multiplication or division, try to convert 6 to 18. Since we have known that we don't use addition and subtraction in creating equivalent fractions, we use only multiplication and division to do that. Based on that, think about how to convert 6 to 18 using either multiplication or division. Obviously, it is by multiplication that 6 will turn to 18. So, what multiplied 6 to make it become 18? Obviously, it is 3. Therefore, let that same 3 multiply 5. Whatever result is supposed to be here where x is. Please, when that 3 multiplies 5, the result should be here. What should it be? 15. Therefore, x is equal to 15. Let me write it. And here it comes. X is equal to 15. In this bracket, we have a statement that shows how we got this 15. Don't forget that I was asking before, what could have multiplied 6 to give us 18? To get what multiplied 6 to give us 18, we divide 18 by 6. See it here. Let 6 divide 18. That is how we know what multiplied 6 to give us 18. And the answer is 3. See it's 3 here. When that 3 is gotten, that same 3 should multiply this 5. That's why 5 is here at this point or location. And that is why 5 is written beside this bracket. Here, from the bracket, we get this 3. And this 5 corresponds to this 5. So 3 times 5 is this 15. So this explains how we got this 15. Let a similar thing take place in the case of second example. Let's find y. Again, how did 5 become 25? In this second case, what is missing is denominator. So we use the numerators to first get the constant factor that multiplies both up and down to get us whatever is here. Again, how did 5 become 25? By either division or multiplication. Obviously, we are supposed to make use of multiplication to convert 5 to 25. What is it? It is 5. That is because if you divide 25 into 5, the result is 5, which means 5 must have multiplied both 5 and 6 to get what is here. Therefore, when 5 multiplies this 6, the result should be here. Now, 5 times 6, what is it going to be? Let me write it here again. And here it comes. The value of y is equal to 30. How? That same 5 that multiplied this 5 to give us 25 must multiply this 6 to give us what is here. That 5 times 6 is equal to 30. Therefore, this y, which we don't know, has become 30. This explains how that was done. For us to get how many times that 5 multiplies to get 25, we just divide 25 by 5. See it going on here. When 5 divides 25, the result is 5. That same 5 multiplies this 6. See it here. And that's how we got 5 times 6. And that is equal to 30. I just hope that what is going on here is clear to you. Can you try this last one? Think about it. All right, let me get the answer. And you compare it with what you have or what you've been thinking the answer should be. And here it comes. You should agree that Z is equal to 35. Why? We ask again, how did 6 become 42? By either multiplication or division? Obviously, by multiplication, 6 must have multiplied 7 to give us 42. The reason is that if we divide 42 by 6, what we get is 7. Therefore, 7 is a common factor that multiplied 5 and 6 to get us the next equivalent fraction. Now, when 7 multiplied this 6, we got 42. When the same 7 multiplies this 5, the result should be here where Z is located. And what is the result of 7 multiplying 5? The result is 35. Therefore, this Z is equal to 35. This thing in the bracket, like before, explains the process. When this 6 divides 42, that is in effort to know the common factor dividing up and down. This is what we did. So when 6 divides 42, it is 7. 7 times this 5 gets us the next one, which is Z, not formerly unknown, but now equal to 35. At this point, please check out for an exercise. And here comes the checkpoint. It says, obtain the values of the missing parts of the following statements of equivalence. I just believe that you can interpret this instruction. With that in mind, the numbers include number I, 3 over 5 is equivalent to C over 10, is equivalent to 12 over E, is equivalent to F over 30. II says 5 over 8 is equivalent to 15 over M, is equivalent to G over 40. III says 2 over 3 is equivalent to 6 over H, is equivalent to 10 over X, is equivalent to Y over 24, is equivalent to Z over 30. This third question highlights the importance of the fact that the number of fractions that are in statement of equivalence is not only supposed to be 4, as we have been seeing all the while. Just like this one, we have only 3. The first has 4 as before, and this last one has how many? 1, 2, 3, 4, 5. We can even have 6 and more fractions featuring in statements of equivalence. At this point, let us turn our attention to lowest terms. What exactly is the link between lowest terms and the equivalent fractions? It has become obvious, or almost obvious. Let us go through it. Now let's talk about lowest term. I asked earlier, what is the link between equivalent fractions and lowest terms? It is because lowest term is found to be among equivalent fractions. One of the fractions which are equivalent is considered to be the lowest term. What then is lowest term? Having known the link between lowest term and equivalent fractions, that is, that every fraction in this lowest term is selected from among equivalent fractions. Again, for sake of stress, that is the link between lowest term and equivalent fractions. Having said that, Let us use this reminder to learn in full measure what lowest term is and how to get it. Don't forget where this array of fractions came from. We recall dividing one orange into 2 and picking 1, into 4, picking 2, into 8, picking 4, into 16, picking 8. At the end of that exercise, we concluded that all these fractions were equivalent, meaning that this fraction and this fraction are just equal in value, despite having different values of numerator and denominator. The same thing is applicable to this and this, this and this. That means that all these 4 fractions are not different. They differ only in the values of numerators and denominators, but essentially their magnitudes are the same. That is why we say that they are equivalent. That is the reminder. Now, from this statement, we learn what is called lowest term. Again, what is lowest term? Before we define it, let me state that in real life, carrying out this exercise, when compared with carrying out this exercise and this, will reveal which one is the easiest. In more practical terms, bringing one orange and breaking it into 2 to take 1 out of it involves some work. The work involved in dividing the orange into 2 and picking 1. Compare it with the work involved in dividing the same orange into 4 and picking 2. Compare it with the work involved with dividing the same orange into 8 and picking 4. The same thing applicable to 16 division portions to pick 8 from them. Which of them do you think would involve the least work? Obviously, instead of wasting time and energy to divide something into 4 to pick 2 at the end, because if you pick 2 out of 4, you have just picked half. If you pick 4 out of 8, again, you have picked half. The same half is what you have picked. If you pick 8 out of 16, you also have picked half. If you had known that all you want is half, why divide it into 4 to pick 2? Why divide it into 8 to pick 4? Why divide it into 16 to pick 8? The easiest would be to divide it into 2 to pick 1. This one, which appears to take the least time and energy to carry out, is the one that is said to be in its lowest term. Therefore, from among these equivalent fractions, the lowest term is this one. With this in mind, how then do we define lowest term? Keep on thinking while I write the definition of lowest term. Afterwards, compare what you were thinking and what you would see afterwards. Let me define it. And here comes the definition of lowest term. It says, lowest term is a form of a fraction in its most practicable state. I hope that statement is clear. We recall that this 1/2 is considered to be the lowest term of all these equivalent fractions. Since they are all equivalent, this one is the one in lowest term. Why? It is in the most practicable state, which means it is more practical to divide something into 2 and pick 1 than 4 and pick 2, or 8 and pick 4, or 16 and pick 8. All of these are practicable. They can all be carried out. But the one that is most practicable is this one. Because of this, we refer to 1/2 as the fraction that is in its lowest term among these equivalent fractions. Now, what if we have a fraction which is not in its lowest term, and we want to break it down to its lowest term? Somebody was told that something was broken into 60 portions, and somebody was told to pick just 24. Somebody wants to know, instead of going to the labor of dividing it into 60 and pick 24, what is the least work he can do in the process? That is, that 24 over 60 is equivalent to what in its lowest term? Let us use it to see how to convert a fraction which is not in its lowest term to its lowest term. Let's find out. And here comes the example. It says 24 over 60, like we heard earlier. Something was broken into 60 and 24 were picked. This is not in its most practicable state. Why? It wastes time and energy to divide something into 60 and afterwards pick 24. It is just better to divide that thing into 5 and pick 2. This takes less time and energy than this. That is, carrying out this exercise takes less time, takes less energy than what is required in accomplishing this one. That is why we say that this is more practicable than this. As a result, 2 over 5 is the lowest term of 24 over 60. Let's see how 24 over 60 became 2 over 5. Notice what may have happened. When 24 is divided by 2, the result is 12. The same 2 divides 60. The result is 30. A common factor can still divide 12 and 30. Of all the possible common factors that can divide 12 and 30, I chose the least, which is still 2. Let 2 divide 12 to get 6. Let the same 2 divide 30 to get 15. 6 and 15 still have a common factor that can divide them. What is that number? At this point, I think we still have only one, and that is 3. When 3 divides 6, we have 2. When 3 divides 15, we have 5. Therefore, 2 over 5 is in its most practicable form and is therefore called the lowest term of 24 over 60. The question is, what mathematical principle empowered me to start dividing this and this by the same number? It is the observation we made at the time we were paying attention to equivalent fractions. That is to say, how to get fractions which are equivalent is that it is either we multiply or divide both numerator and denominator by the same number. We just practiced getting equivalent fractions by multiplication. If you want to get the lowest term of a fraction, practice division, the second method. And that is what has just gone on here. So that fact empowered me to divide 24 and 60 by 2, 12 and 30 by 2, 6 and 15 by 3 to get 2 over 5. At this point, there is no other whole number that can serve as a common factor to 2 and 5. And this is why we can't go beyond this 2 over 5. Consequently, 2 over 5 has become the lowest term of 24 over 60. Let us see another example. And here is a second example. We want to reduce this 40 over 72 to its lowest term. Again, empowered by a mathematical principle we just learned before, we divide 40 and 72 by a common factor. Let us divide with 2. We know that there are some other factors we can make use of, but we choose the lowest here of all the common factors. When 2 divides 40, we have 20. When the same 2 divides 72, the result is 36. We now have 20 over 36. This is yet to be in its lowest term. Further, we divide 20 and 36 by another common factor. Let that common factor be 2 again. Despite the fact that we have other common factors, apart from 2, 4 can still go. But let us use the lowest of all the common factors. 2 is that lowest common factor of all. Let 2 divide 20 to give us this 10. Let the same 2 divide 36 to give us this 18. Alright, we now have 10 over 18. This is yet to be in its lowest term. Again, do 10 and 18 have a common factor? Yes, they have. In this case, they have only one common factor. That is the whole number. That common factor is still 2. Let 2 divide 10 to give us this 5, and let 2 divide 18 to give us this 9. 5 over 9 no longer has a common factor for numerator and denominator. 5 and 9 do not have another whole number common factor. Because of that, dividing something into 72 and picking 40 is done in the most practicable way by dividing the same thing into 9 and picking 5. This is more practicable than this. We then say that 5 over 9 is the lowest term of 40 over 72. And that is it here. The lowest term of 40 over 72 is 5 over 9. You can agree with me that this process is a long process. Can this process be shortened? Yes, it can be shortened. This intermediary method of dividing each time with the lowest common factor takes space, takes time, and takes more energy. Is it possible to find a way of cutting the process short and still get the correct answer? That is the correct expression of a fraction in its lowest term from existing one? Yes. How? We now go to second method of getting the lowest term of a fraction. So far, the method we have been using is called the lowest common factor method. That is LCF method. Let us now use the HCF method. Again, the method we have been using till now is LCF method. That is lowest common factor method. Why? Of all the factors of 24 and 60, we chose only 2. First, do you know that 2, 4, and other higher factors are all common factors of 24 and this 60? In fact, let us list all the common factors of 24 and 60. And then from there, we choose second method, which is quicker. Here they are. The common factors of 24 and 60 are 2, 3, 4, 6, and 12. Do you agree? That is, at the same time, 2 can divide 24 and 60. At the same time, 3 can divide 24 and 60. At the same time, 4 can divide 24 and 60. At the same time, 6 can divide 24 and 60. At the same time, 12 can divide 24 and 60. There is no other factor, that is the whole number, common to 24 and 60. So these ones are the only whole numbers which are factors common to 24 and 60. Which one out of these common factors is the lowest? It is 2. 2 may stop being the lowest and 3 can turn to be the lowest. For instance, here, when it came to 6 over 15, no longer was 2 the lowest common factor. It became 3 because 2 is not common to 6 and 15. Instead, 3 is common to both of them. So that 2 is the lowest common factor is beginning from here. But as we progress, other numbers will become the lowest common factor. Which one of them is the highest common factor? That is, of all these common factors, which one is the highest? It is 12. If we divide with 2, the lowest common factor, we get the next fraction, which is not yet in its lowest term. If we keep on dividing with these lower factors, we keep on getting fractions which are not yet in the lowest form. But if we divide straight away with this 12, we can get just 2 over 5. Let me write that. Now we say, most quickly, 24 over 60 is just equal to 2 over 5. Just from here, straight to this point, cutting off these two intermediate steps. I think this is far better than this first method. In the first method, I kept using lowest common factors. In this second method, I used the highest common factor. So the use of the highest common factor is faster and more convenient than the use of the least common factors. Therefore, I just came here and used 12 to divide 24 to give me 2. I used the same 12 to divide 60 to give me 5. Straight away, 24 over 60 became 2 over 5. You can now agree that of the two methods, the quicker one or the more convenient one is the use of the highest common factor. Whichever way, whether it is the lowest common factor or highest common factor, you can express a fraction which is not in its lowest term in its lowest term. Use either the lowest common factor approach or highest common factor approach in tackling the exercise that follows. And here is the checkpoint. It says, using both LCF and HCF methods in each case, reduce the following fractions to their lowest terms. Number 1, 72 over 120. Number 2, 54 over 144. Number 3, 64 over 80. Number 4, 150 over 210.